Yeah, hi, I'm Milena. And we have a lot of information in just a short amount of time. And I'll step away from my computer because you won't see me out behind us. We're going to talk about human learning today. And you might think of mean school teachers, old school books, and dirty school bathrooms. But this is not what we're going to talk about today. Learning is something different. Learning actually is, and right now the pointer is not working. I just checked it. All right. It's the acquisition of knowledge or skills through study, experience, or being taught. That's just a very simple description. And you might still wonder, why are we talking about learning here? Like, we are all software developers. We have studied all our lives. So let me give you 3 good reasons why we have to talk about learning. The first one is that we are in an industry with a high need for learning. So actually, scientists consider that there's a half-life of knowledge. So over time, knowledge evolves, it changes, marginalizes. We have new facts that we learn, and old facts are consumed into them. So actually, you might wonder why kids in school still learn how to read maps, even though we do have Google Maps. It's because we still, in our educational system, try to prepare our students with old knowledge. So in case really all servers or all power lines crash, we still have some fundamental knowledge for survival. And actually, if you look at the half-life periods of certain domains that they figured out, you can see that while elementary school knowledge actually stays with us a long time, in the technological or IT fields, we have one of the lowest half-life knowledge. So we have to constantly keep up with the industry and learn, and I assume this is why you are here as well. The next one is that machines are learning now. So learning has become a completely new topic of study. And actually, if we look at one of the smartest private students, ChatGPT, he was trained by reinforcement learning with human feedback by human AI trainers. And if you don't have a clue what this means, you will know after this talk. And reason number 3, we have used nature as our template for amazing and very cruel innovations. So we look at birds, and we invented aerodynamics. We took a lot of concepts from there. Like, I'm a swimmer, so I often like diving with fins because it makes me faster. Same as fish do. And we used molecular structures to come up with atomic design patterns, which we're now using in the UI. And neuro and cognitive sciences, the field where I originally come from, gave us some concepts that we are now using in AI. So learning is very important. And just to summarize what we have learned so far, learning is a lifelong process of keeping abreast of change. And the most pressing task is to teach people how to learn, which we're slightly going to do today. And we're going to start with a very simple task. So when I was a student, I was working at an ice cream shop. And me and my colleagues, we came up with this order of the ice cream flavors. So I'm behind the counter there. That would give us a more efficient workflow because you are dealing with a lot of guests here. So I kindly ask you to remember the order of the flavors. You have 1 minute for this. All right. minute is over. So there will be a test later. You will have to leave the room if you... No, I'm just kidding. No, don't worry about it, but there will be a test. Okay, so now we're going to look at the process. This is actually the processing information theory. So what actually does happen in our brain on a very superficial level. So we do have the ultra short-term memory, which is basically the first area where information enters your brain via your senses, which are basically your input modalities. And here we decide via attention whether we want to take this information further. So if you're currently studying and all of a sudden you hear a fire alarm, then the sensor memory and attention are going to decide, you know what, stop learning. I don't care, we have to survive, and the information will be passed. So attention currently has become a very important topic. Who has read the paper, Attention is All You Need by Google, which actually made Transformers? Okay, I'm always like really disappointed in how little we know about this. But yeah, basically attention works slightly different there, and they have multi-headed attention, which is so cool because they have like multiple people with attention. But attention is there to actually filter what is important, what is not. So if it's not important, it will be dropped. And actually you drop things all the time and you don't even know about it. But if something is important enough, it will finally make it into your short-term or working memory, which basically is the CPU of the brain. So from here, information will be processed further. So I'm just going to put some more information in our short-term or working memory until we have it filled up. And now what happens from here? So with this information, we can do a lot of things. But what we really want to do is process it. And if we want to learn, we want to connect it and maybe keep it for longer, like your mom's birthday. You want to keep it forever in your memory to process it further. So here we have our long-term memory, which basically is our knowledge base. And you don't just want to throw things in there. Imagine it to be like a huge library. And you don't want to just put books in there. You'll never find them again. So you need to come up with some kind of order, which are schemas in our brain. So you have schemas there already. Everyone has schemas. We'll come to that in a second. But what you do now with these chunks of information, you either add them to an existing schema because they perfectly fit in there, like the thriller section. You create a completely new section of historical dramas because you didn't have that yet. Or you just loosely couple it, which is the last thing, because it does fit there, but not exactly well. But actually, this perceiving and chunking of information is something we do every time we learn something, whether you do it on purpose or not. So every time you learn something like you do right now, probably leads to a restructure of your brain. You can't do anything about this. And what's also really interesting is that this whole process is very computational and expensive. So when your parents told you, hey, explain it to others and you will actually get it in your mind even better, no. Studies could show that while you explain to others, you're so focused on explaining to others that you actually don't learn anything from it. So that's a learning myth actually we have here. All right, so in the field of AI, for a long time, it was split up into two areas of research, which was the knowledge engineering, which is exactly the how do we actually get things into a knowledge base? So how's knowledge being created, fed, and processed? For example, by big data, so connecting to huge data streams, or by exploring the environment. Topics you might have heard of here are k-nearest neighbors, support vector machines, or clustering. And the other big part of research was knowledge representation. So how is this stored knowledge actually later then perceived so we can actually use it? So topics here are propositional logic, search rooms, Bayesian networks, or knowledge graphs, which are still pretty common topics right now. So let's look at the whole learning process, and there's 4 things we're going to look at. And the first one is going to be the data. So clear up on some terminology. I'm pretty sure you are all aware of this, but just so we have, when I talk about it, the same picture in our minds. So data can lack context. So it's just singular pieces or fragments of information like a letter. Then we have information. So information gives context to the data. It's prepared data, so that would be a whole word made of letters. And then we have knowledge. So this actually brings depth and understanding in such information. All right, so data, so basically really plain letters. How do they actually get in the system? Just a reminder from like third grade, our senses are touch, sight, hearing, smell, and taste. So this is our input modalities. So every day you take stuff in, you take data in, and you might have seen these mediums where data is presented for you. I think everybody has some kind of go-to, like some go to Stack Overflow, some might go to Wikipedia, some might go to their personal documentation, animations, Udemy, whatever you do. And then also a lot of people believe that for everybody that's very different, which we all have cognitive differences. But who believes that there's different types of learners? So that there's people who can better learn visually and some more like the auditory. Who believes that? Hands up. All right. Yeah, I'm going to disappoint you, but we're going to talk about something else first. So what are actually the senses of an artificial agent? So we distinguish between software and hardware agents. Software agents, they have a very plain input modality like ChatGPT, you type stuff in. It's not very natural, but we also have hardware agents. And they actually do have sensors, so they can get information from the environment without you giving them explicitly to them. So they have cameras, pulse monitors, microphones, and then also they have actuators, so they can play with the environment, like speakers, vibration wheels, or vacuum cleaner Herbie, who likes to eat my socks. He can do that. So let's look at the question I asked before. The most suitable external representation does not depend on the learner's preferences. There's no single study that actually hints into this direction, and it's still a common myth among teachers. So a lot of teachers still think that, and a study from Harvard could actually show that most teachers still believe this, which leads to a lot of misunderstanding of students. But what is actually important when we try to get data in the system? It's the kind of information that we want to transfer. And I'm going to show you this in an example. So we have many kinds of ways on how we can present information to people. We can do this by linguistic ways. We can do it by natural language, by speaking, audiobooks, podcasts. We can also do it by formal language. So when I play my clarinet, I use a music sheet. When I program, I do it in a programming language. And then also we have visual information like logic images, analog images, or realistic images. So usually when you enter a building, you don't get a brochure that tells you what to do in case of an emergency. That would completely slow you down and you will never make it. So usually you get very straightforward signs that are international that give you the information of what to do in an emergency. So we have different ways on how to represent data. And just another example, so what makes a good representation of data? So if you look at this, and I'm going through London, and I'm like, oh, when does the next bus go to the British Museum? Someone is going to give me a written timetable. When I ask how can I walk there, they are going to show me a map. And when I ask how to find the bus, they're probably going to show me a picture. So I need something that is computational efficient. I don't want to think about it too long. Then it has to be performant. So there shouldn't be this ambiguities. Like when you tell me, oh yeah, there's a big bus around the corner. I'm like, which corner? What is big to you? So it's like very relative. And then of course the completeness. So is it actually giving me all the information that I need? So why is that so important to humans? Because we are limited in capacity, just like machines. So working memory can process from 5 to 9 chunks. So we have this limitation. And this limitation is now consumed by 4 kinds of load, which I'm going to show the 4th later. But the first 3 are the extrinsic load. So actually, how hard is it for me to read the representation of the data? The second one I can't really do anything about is the intrinsic. Learning polymerase chain reactions is just a little more complicated than French vocabulary, just from the domain complexity. And then we have germane load. So this is what the brain is consuming to actually process the information. You can't do anything about that. That's just your brain. But what we can do is we can do something about the extrinsic load. And you have heard all of the things I'm going to tell you in a second from clean code, actually. So we want to reduce extrinsic load, and there's important principles. One is the coherence principle. So when you learned the order of the ice cream flavors, I could have told you about vanilla. When you threw down the vanilla in my ice cream store, you really got yelled at. Vanilla is freaking expensive. That's really interesting, and it's also really interesting that I have been traveling to Greece, but it's just an impairment. You don't need to know this in order to learn the ice cream flavors. So The next one is the redundancy principle. Don't repeat yourself, especially don't make it in different modalities. It's not going to help anyone. We find this in code all the time. And the third one is the spatial and temporal contiguity principle. Things that belong together should be presented together, locally and temporarily. So if I give this to you like a little bit further apart and later, you're not going to see the connection. So typical quality issues that we also find in our repos are duplicate instances, missing packages or documentation, or various terms, technical or domain terms, which they all lead back to these principles because we are the ones working with the code and not the machine. So yeah, don't be responsible for your colleagues' headache. Think about how humans process information. So if we have bad data, you know what this can lead to, and that's why this is important. It leads to limited trust, confusion, and also, of course, poor decisions. So what is high quality of data? Just to sum this up, it has to be fit for its intended uses and operations, decision making, and planning. All right, we're going to go back to the next chapter. So how do we actually process the data? And there has been a very important theory in psychology, which is the cognitive theory of multimedia learning. So when you get information in by a representational encoding, it can be, and these are the most research channels. Of course, there's like tactical and that kind of stuff as well. But you have words or pictures, usually some form of this. So words can also be consumed by your eyes if you have a book. But later on, they will be put in a certain channel. So even though you read the text, they will come into your sound channel and be processed in the verbal mode, while pictures will be actually processed in the pictorial mode. And there's something in the verbal mode, which is called the phonological loop. So if you try to remember a phone number, you're probably going to repeat it in your inner ear over and over. You can actually hear yourself do this. Well, if I ask you to remember my face, you don't have to do that right now, but if I ask you to do that, you will try to form a picture in front of your inner eye, which is the visuospatial sketchpad. So you process these things differently before they actually enter your long-term memory, if they do. And what's really important is you can use both channels at the same time, but you can use one channel for more than one information. So what's really good is if you watch a documentation with some subtext that's spoken. What's not good is if you're programming and try to hear podcasts on the side, because it consumes the same channel. All right. So looking at that, okay, that's a combination. And let's look at how, what are the storages? Where do we actually store the data then? So I already told you there's a sensory memory, which just has information for a very short time until it's decided whether it's processed any further. We have the working memory, which has information from 15 to 45 seconds. And we have the long-term memory, which keeps information for 1 second, yes, very short, to a lifetime, which is pretty cool. And it has unlimited capacity, which we don't know if it's really unlimited, but none of you is ever going to use up their whole long-term memory storage. If you do, tell me. That's going to be a very interesting research question here. And what's really, really important is to get stuff in the long-term memory. Our brain is so smart. So it tries to figure out what is important. What should I actually store long-term? Like, again, my mom's birthday, because surprisingly, it occurs every year. And I might need it next year again. So in order to get 12 loose syllables in the long-term memory, you need to have 17 repetitions. So the more often you encounter the same information, the more the brain thinks it's important and will store it longer. Which is also really important, and I don't know if AI can do this yet, is forgetting. We sometimes forget how important forgetting is because it cleans up our storages from things that are just not important. So that's pretty cool. All right, now there's the test. Let's see how well you did. Just scream the ice cream flavors. What's the first one? Some swarm intelligence going on here. Okay, next one. Next one. Yep. Nice. Nerds. Yeah. Yep. Perfect. Oh my God. Yeah. Okay. You guys are real. Okay, we can stop now. No, I'm just kidding. All right. So how do we actually organize knowledge? I was talking about schemas before, and what is a schema? A schema is a cognitive construct which organizes information in order to store it in the long-term memory. So necessary steps to do that are first elaboration. So we connect it to existing knowledge, and the second step, which I already showed, is induction. So we convert it, and this is what we haven't talked about, is to convert it into a more abstract scheme in order to reuse it later. We don't only want to learn facts. So when you did that a second ago, some of you might have applied existing schemas already. So let's see, maybe you have the same schemas as I do, which I have the schema of dangerous flavors because they contain allergic things or alcohol. Then I have the basic ice cream flavors. I do have the concept of berries, the concept of fruit, and the concept of vegan. Depending on culture, gender, country you come from, you might have different schemas. Who applied schemas? Okay, that's a lot. Some might have not because of time restrict. Then sometimes we use different learning strategies, but usually we do apply schemas, which is really cool. And actually, we're now going to look at how an artificial agent would do it, because for you, it seemed pretty natural to do this. You have these existing schemas, but an artificial agent doesn't have them out of the box. So when you go into a supermarket, or imagine you went when you were like 4, you couldn't read, and you looked at magazines, and you really didn't care about the kids section, where it was all really colorful and just pictures. But then when you grew older, you started to see, oh, there's different magazines. There's sports magazines, car magazines, fashion magazines. And then you finally understood why a magazine called Playboy with a little bunny was not in the kids section. So you figured it out over time, but an agent has to do that too. And one very simple thing to do that is the naive Bayes classifier, which is used for detecting content or for classifying content, for email spam detection or sentiment analysis, which we constantly do using AI. Actually, Gmail does it. So sentiment analysis basically means if your boss sends you a text message, then the AI can tell you whether he's about to fire you or if you get a promotion. So who has actually seen this formula? Nice. Depending on country, you should have seen it from 8th to 10th grade. This is where math actually gets a purpose in life. So we're going to look at that. And this is the Bayes theorem. Actually, the whole naive Bayes classifier is based on this very simple formula, which is really cool. So we're going to do that right now. We're going to do some math. So I have 2 kinds of magazines. I have car magazines and a fashion magazine. And I'm asking the agent to please classify what kind of magazine he's seeing, a car or a fashion magazine. So usually we have more than one word in a magazine, but let's just now imagine they have not much text. So we have one magazine containing beauty, one containing hot, and one containing hot beauty. And I now want him to classify what type of magazine is this. So I know there's 40% of car magazines on the market to 60% of fashion magazines. And then I give him the probabilities of how likely a certain word appears in a certain magazine. So hot being in a car magazine is just a 20%, and then I have hot being in a fashion magazine, which is just a 5% probability for being there. So now, since I do something called Laplace smoothing, I'm not going to go deeper into this. I can actually ignore the denominator, just so you're not confused. I multiply these probabilities, and I get to the conclusion that if it's containing beauty, it's more likely to be a fashion magazine, while if it contains hot, it's more likely to be a car magazine. But if it contains hot beauty, I multiply these probabilities, and I get to the conclusion, then that's probably a fashion magazine again. So this is pretty simple. I can derive the category from that, and that's it. But the main question is, how did he get these probabilities? Because I told him. I told him what the market looks like. And I told him how likely a word can actually be in a magazine. And this is still information that we label for this agent and that we give to him. So he needs some kind of teacher that gives him the information, that makes a test with him. And if we have a smart model that keeps learning, he will actually adjust these probabilities with every estimation he makes, and he will get better. Yes. So Another thing is that these schemas that we have are now interconnected. So if I have the schema of fruits, which is most likely connected somehow to the schema of vegetables. So we have a huge network, which again depends on our personal experiences that we made in our life and what we have learned. These are two of the semantic networks that I have in my head, and I'm pretty sure you somehow do them too. You have them too. And now, a fun fact: sometimes you learn things you don't want to learn. And marketing uses this to hack their way into your semantic network. So maybe you can see what brands are hacked in these two semantic networks. Think about it a second. Yeah, sometimes when I'm at Christmas and I'm watching a polar bear documentation with my family, this brand will randomly pop into my head, which marketing made a good job. Yes, first one is Coca-Cola. Yes, second one. Correct, yes. So that's actually pretty sad. If you want to hack your company into a semantic network of an AI agent, you should probably start now. But yeah, actually, we do form these connections, and they're, again, very different for each of us. But they help us learn. So what's actually going on in the brain when we form these connections? We have 100 billion nerve cells, neurons, that communicate. And there's two main processes involved. So we have neuroplasticity, which means that every time you do something, more neurons become connected. So when you learn how to play a violin, every time you do this, certain neurons are getting more attached and your network is getting more dense. And then we have a second one, which is called neurogenesis, which says you can form new neurons your whole life. So you're not born with a certain number of neurons. And really cool about this is, yes, learning will get harder by age, but both of these biological processes will not stop. So you can learn till the very end, which is really cool. All right, third chapter, knowledge transfer, and that's really, really cool. So we have three types of knowledge. We have factual knowledge, like the first computer mouse was made of woods. That's a fact. I can learn that. Next one is metacognitive knowledge. We'll come to that in a second. And the third one for this chapter is procedural knowledge. So I want to have knowledge that is not like a fact, but that I can use over multiple contexts. So I have abstract knowledge. If in a math class, your teacher taught you about the binomial formula, and they didn't give you any application, you're like, okay, why did I learn this now? Can I forget it now? I passed the test. They teach you without any context, which makes it inert, and you will forget about it. But if it's teach with a context, with an actual application, you understand what you learned it for, and you can abstract it and use it in different contexts, which is so cool. You know that some animals have a skin color which totally fits the nature, so they cannot be seen by the enemy or prey, which is a really cool concept, which we transfer to the military. So we have clothes there, camouflage, so you cannot be seen by your enemy or prey. This is abstracted knowledge that we took to another context. All right. So really nice here. Tell me and I forgot, teach me and I remember, involve me and I learn. This is already what Benjamin Franklin said to this. So we have three types of transfer. We have zero transfer. You all have this colleague that you explain to 3 plus 2 is 5. Now what is 7 plus 5? And they're like, they didn't get the concept. There is no transfer. Then you have negative transfer. So sometimes learning something can hinder you from learning something new. If you have worked with a Windows laptop for 10 years, learning how to work with a Mac becomes really hard because you already have concepts in your head which hinder you from learning, and actually you have a negative transfer. And the third one is a positive transfer, which, as an example, a software architect needs to have a very positive transfer, taking software design principles to any given system. All right, now what can we transfer from here? This is free knowledge from me. If you ever open an ice cream store, take this to whatever flavors you have. Place popular flavors where they are easy to reach. You constantly need vanilla ice cream for basically everything, so place it where it's easy to get. And the second one is place flavors with similar target groups together so the vegans don't encounter all the others. And that's just really useful tips that you can transfer as knowledge and take it to any ice cream store. All right. Chapter number 4. We have to monitor this process somehow. So when we're in school, we have a teacher, we have tests, and we have parents, and they all look at our grades and what we do. So we are constantly supervised and regulated. But once we grow older, we have to be on our own. So you are here because you decided you wanted to learn something for yourself. And later you will evaluate if this has actually been useful to you. So you plan, you set goals, and you come up with strategies on how to reach them. You act, so you actually do what you have planned, and then you evaluate if the performance is what you wanted to achieve. So you do this, and actually OECD PISA, when they measure kids in school, do not measure how much factual knowledge every student has, but they want to measure how well you are at studying, so how well you learned how to learn. Because as you look at the halftime of knowledge, this is really important. So actually there's like a lot of stuff going on in your brain when you learn because you're monitoring and evaluating the whole time. And we're not going to go into much detail here, but while you're learning, you're constantly checking on what you're actually doing. And this is where our fourth load comes in, the metacognitive load. And now we have all the loads. So yeah. All right, so I want to say a little bit about time management, because when it comes to learning, this is a major issue. We all know this. So first, there's the discrepancy reduction model, which states that usually when you start learning for an exam or for some test at work, you usually start with the harder items. So you want to learn the hard ones first, and then you go to the easy ones. Except for the shift to easier material effect that comes in when you have a restricted amount of time. Then you tend to do the easier items first because you're like, okay, I don't care about the grade, I just want to pass. So just give me the easy stuff so I can pass. And then there's the theory of optimal learning. So do not overlearn. It doesn't really help you to learn like the crazy 100 facts on the world if they don't give you anything. So optimal learning is keep the margin return high. So learn what you really need and do not learn too much. So actually do machines learn self-regulated? Can they learn without a teacher? If we look at it, if we give them a task like classifying, calculating, whatever we want a machine to do, we give them training data. So we tell them, hey, look, this is what I want, this is what I give you, this is what I want to have later, this is the goal. And then you give them some learning conditions, some functions. Right now, they're pretty good at figuring out their own functions. And then later, you test them. So you give them some test data and see if they have done well or not. So who evaluates this? Who constantly gives them the things to learn on, who tells them what to learn, and then who gives them the test? So they still do need a teacher. They're like kids in school. And yes, we do have some kind of unsupervised learning in machines because we are at this point right now, which is pretty cool. But still, it's not the same as self-regulated learning, as we can do set our own goals. So we can do that. So so unsupervised learning means without human intervention, not without human supervision, actually. And examples for this are clustering unlabeled data. And one we have here is reinforcement learning. This is also what ChatGPT is using. So the agent can act within its environment on his own. He can explore. He makes decisions on his own, but he will receive feedback from human beings, whether he did good or bad. So he's not completely without supervision. And he is based on deep learning. So this is also a mostly unsupervised approach, which is really cool. It's a subset of machine learning, one we saw earlier. The naive Bayes classifier is a full machine learning model. Pretty simple, but still. And he is based on neural networks. And neural networks, again, use mechanisms from the era of learning. So they activate functions and weights. I'm not going to go into much detail here, but you give them some input, and it travels, and there comes some output. What exactly happens in the middle, we are not going to approach today. But what they do actually is they check later, is the output what I expected? And if not, please adjust what you have been doing and see if you are better next time. So there is some trial and error learning here. And also they have a learning rate. So if they see, hey, you're not making any progress, we need to slow down here. It's again the same as you do with children in school. So you adjust a learning rate. All right, so JPT, just to summarize this, he had some private training in the woods. So he was trained on test data, instructions with a teacher, actually a human teacher. And then later he was sent into the environment to make it on his own. And he does this more or less good. He survives. So let's look at the outcome of learning. So can we actually measure the outcome of learning? And this is where intelligence comes in. So we're just going to talk about intelligence real quick, which is a huge topic, I know. So who thinks they're highly intelligent? There's one person that admits. I know everybody here believes that. Like, let's be honest. Every human being thinks they're more intelligent than the others. And who knows what intelligence is? Yeah, exactly. So it's actually not that easy. I found over 30 official definitions of intelligence, so it's really hard to grasp. And usually we consider intelligence as what we measure in an IQ test from psychometrics. So psychometrics is an area where we test mental states and cognitive abilities. And we do have not only one IQ test, we have like dozens for multiple intelligence theories, and we're going to look at some today. Intelligence is much more than an IQ score. That's important, and that's in science just like an agreed on thing, so we are sure about that. So in Latin, actually, intelligere, that's where intelligence comes from, means understand and comprehend. And if we look at the definition of learning again, which is the acquisition of knowledge or skills through study and experience or being taught, I liked this definition of intelligence the most, which is the ability to acquire and apply knowledge and skills. So often, intelligence is seen as how good we are at learning. So that's a very interesting definition here. And now looking at artificial intelligence, there's even more definitions on this. But one that I thought was really interesting by Russell and Norvig, who have been in this area for a long time, is that we distinguish between systems that think like humans, systems that act like humans, that think rational, and that act rational. We are right now back to the systems that act like humans. We're far away from systems that think like humans. Some might consider this as weak and strong artificial intelligence. But yeah, here you can see the spectrum. But what I think is really interesting, that we always refer to human beings when we try to define things from the area of AI. All right, so I'm going to show you two theories. There's a lot more. These are two of the most famous ones. One is from Sternberg. So he defines intelligence as the ability to achieve success based on your personal standards and your social cultural context. So he distinguishes between analytical intelligence, what you can measure in a test, creative intelligence, so your imagination and creativity, and practical intelligence. So how good are you in surviving in new situations that you put yourself in life? And the other one, which I really like, is the theory of multiple intelligences by Howard Gardner, who splits it up into 8 different types of intelligence, which you have the logical, mathematical, the linguistic, the interpersonal, and the intrapersonal. Which one you really consider as intelligence and you value depends on the culture. In Western societies, we value the first two the most, while in Asian cultures, they also very much value these two. The next 4 are the musical, bodily kinesthetic, visual spatial, and naturalistic, which the first 2 are highly valued in Bali because dancing and music is very important to their culture. And the islands in the bodily kinesthetic and visual spatial are very important for islands in the Pacific, as they admire people who can steer a boat through a storm without having any compass or maps. So it really depends on the culture. And then, of course, we have emotional intelligence, which perceived a lot more acknowledgement in the last couple of years. It's the ability to monitor one's and others' emotions, use emotional information to guide thinking and behavior, and distinguish between emotions and label them appropriately, which is so important for your self-awareness, self-management, and social awareness. And actually, it has been shown that people who have a high emotional intelligence are much better at actually achieving their goals and can better resist stress, which is really important as well. Okay, so are we born intelligent? Race and gender do not have anything to do with it. There's no studies that show this, actually, but there is some kind of genetic influence. Scientists are not sure about this. It has been used in very bad ways, so I just ignore this for now. But there have been correlations found, like a low birth weight and bad health conditions, that lead to a lower measured IQ, a socioeconomical status, as well as low self-awareness, and the circumstances when taking the test. So usually girls under stress have a lower measured IQ, which is not about their brain or about their cognitive abilities. So environmental circumstances do influence at least the measured IQ. That's what we know so far. Okay, but in general, scientists found out that your brain does have a capacity for learning that is virtually limitless, which makes every human being a potential genius. And we're right before lunch. I'm just going to do the last 2 slides. Intelligence is expensive. So if you look at ChatGPT, you might think, oh my God, they spend so much money on this. It takes about $700,000 to operate and 3 to 5 million to, that's my alarm. I'm so sorry. Okay. It takes 4 to 5 million to train this. But if you look at expenditure on education, which is the fundament of intelligence, look at how much we spend here. The EU alone spends 4.8% on their GDP, so $700 billion on education. And education still is a basic human right. So we as humans, we have a motivation to learn. We have goals and dreams, what we do this for. But what are the goals and dreams of machines? Why do they learn? And sometimes I don't understand why we actually care about even making machines learn, as long as not every human being has been enabled to. In Afghanistan right now, over 2 million girls have been deprived from their right of education by Taliban, which is so sad. And this doesn't have any religious or cultural reasons. It's just because some evil human beings know how powerful human beings can be once you let them learn. All right, thank you so much.